One of the more perplexing things in physics is easy to ask but hard to answer. What is light? Is it a wave or a particle? Sometimes it's a wave, and sometimes it acts like a particle. The truth is, it acts as both. We just see different properties in different situations. Let's examine each attribute separately. The particle nature tells us that light travels in a straight line. This happens at a very high velocity, a velocity that's constant throughout the universe, so we use the letter c to indicate the speed of light. This allows us to use our average velocity equation. V is equal to delta d over t. We can use this to find the distance light travels and the time it took to get there. The particle nature implies that light travels in a straight line. This is much like a tennis ball traveling in a straight line. It can be blocked by something, or it can reflect and bounce off, as is the case with a mirror. We'll talk about mirrors and lenses later. Where the light gets blocked, there's nothing to shine on, and we get a shadow. For quite a while, light was treated as a particle. However, in the mid-1800s, it was proven, finally, after much controversy over decades, that it was also a wave. In the 1800s, physicists were able to show that if an electric field is accelerating, it creates an accelerating magnetic field, which then accelerates and causes an electric field. This means that electromagnetic waves and light are self-propagating and need no medium to propagate. They can travel in the vacuum, which is unlike all the other waves we've studied. So what evidence is there that light is a wave? If you shine light in a prism, it'll come in, bend, and then bend again. Recall that waves can bend around edges. Imagine water waves coming towards a seawall with a hole in it. When the wave passes through the hole, friction on the edges causes the wave to bend. If it were a particle, it would travel straight through, not bending. What happens if there's two holes? A particle would go through one or the other, but not both. A wave, on the other hand, would travel through both of the openings. This causes two waves which interact in different spots, causing constructive and destructive interference. For light, if you put a screen where these waves interact, you can measure how bright they are. This is the famous double-slit experiment that shows that light behaves as a wave. This led the way to modern physics and quantum mechanics. There are other ways to see this effect for yourself. When passing by small enough objects, light will bend as if it is a wave. For example, a red laser pointer pointing at a human hair, which if we graph the brightness, we can see as the same pattern, just like the wave example earlier. This means we can use some of the equations we learned earlier for waves with light, keeping in mind that the speed of light is constant. This is an equation worth remembering. Keep in mind, since the speed of light is so fast, lambda is going to be very small, but the frequency very big. We also can find how much energy light has. This depends on Planck's constant and the frequency, where Planck's constant is equal to 6.6 times 10 to the minus 34 joules times second. This is an incredibly small number, which means that a single photon, a particle of light, does not have a lot of energy by itself.